This is Peggy Lohman. I'm one of the marketing professionals here at the Object Management Group, or you might know us as OMG. I'd like to welcome you to today's IBM Rational webinar titled Techniques and Benefits of Incorporating Safety and Security Analysis into a Model-Based System Engineering Environment. And with that, I'd like to turn the program over to Gavin Arthurs. He is a solution architect, systems engineering with IBM Software Rational. And Gavin, if you'd like to just go ahead and move forward, we'll be paying eager attention. Thanks.
Okay, thank you, Peggy. Thanks everybody for showing up here. So I've got quite a few slides, so I'm going to go through them quite quickly to get under the time we have here, about an hour.
The broadcast is now starting. All attendees are in listen-only mode.
Okay.
Hopefully we'll have some
Let's
questions.
go ahead. Sorry.
Yeah.
So this is Peggy Lohman. I'm one of the marketing professionals here at the Object Management Group, and you may know us as OMG. I'd like to welcome you to today's IBM Rational webinar titled Techniques and Benefits of Incorporating Safety and Security Analysis into a Model-Based System Engineering Environment. And with that, I'd like to turn the program over to Gavin Arthurs. He is a solution architect, systems engineering with IBM Rational Software. And Gavin, if you'd like to take over, we will hand it over to you.
Thanks, Peggy. So I have quite a few slides here. We're going to get through them pretty quickly. We'll have to go through them quickly to get under the time. And the presentation, I believe, will be made available to you either, I think, on the OMG website, or you might get a follow-up email.
Yes.
So you can review them then. So as the title said, I want to talk about a few concepts around incorporating some safety analysis techniques into a model-based, specifically a model-based system engineering environment. Why is this topic important? Well, there are plenty of examples now where there have been examples of incidents, failures that are a result of complexity in the system around how systems interact, the internal components of a system interact, as opposed to just simply a failure. Two here I have listed: the V-22 Osprey. There was an incident where some folks, the pilots, were killed, and in this example there was actually a failure, a hydraulic failure that you could have pointed to. There was a hydraulic line that failed, although the system was designed to accept or survive that kind of failure. The problem occurred really between the interaction of the pilot and his set of procedures and the flight control system. If you notice here in the description, the pilot had 8 attempts of resetting the software, which he was required to do, but each time he did that, the system went through a reset which slowed the plane down. Eventually it crashed. And again, this will make a little more sense as we go through some other examples in a moment. The Mars Polar Lander, this was a case where as it was coming down to touchdown on Mars, the legs, the landing feet deployed, which created a vibration in the system in which the computers thought it had actually landed, and so it turned off the descent engines, and it ended up falling, and they lost it. And this despite the fact that the designers knew that the legs would produce this kind of vibration. The software was written to detect vibration and interpret it as landing. So in this case, this nothing failed per se. Everything worked as designed. This was really a condition of a situation where we had two systems interacting inappropriately. Typically when we talk about this subject, because there's some variability in understanding of terms used, I'll lay out some definitions that are used throughout this presentation. I won't go through all of them. The one I'll bring attention to is this concept of fault and the fact that there are two main kinds of faults. One being a failure, which is something that most people associate with safety, so the failure of something in the traditional engineering sense. The other kind of fault is an error or a systemic fault, which is really the focus of this presentation and the issues around that. This is typically a misunderstanding in requirements or in the design, and specifically, for instance, software really only contains faults that are errors, since it does not fail per se. The other thing to differentiate here is the separation of reliability from safety, and there are two distinct concepts which are oftentimes confused and looked at in the same way, and I think it's important to keep them separate in your head if you're going to do a good job, especially at the systems level, and we'll see that here in a little bit. Now, the title does include the word security, and in the interest of time, I'm not going to talk too much specifically about security, although from a systems perspective, safety and security can be handled almost identically. So many of the concepts I'm talking about here, especially around a systems approach to safety, would apply directly to security concerns. The differences are going to be in the specifics, the detailed implementation of those concepts in the ultimate design. Now, the traditional hazard analysis technique out there, fault tree analysis, you'll see used if you do searches on safety analysis. The fault tree analysis is a tried and true mechanism for doing that. And this was developed in the 60s. Bell Labs, what it is a top-down search where you identify a hazard and then you build a tree underneath it to explain the possible combinations of things that could lead to that hazard using some booleans and so forth, and there's an accepted set of graphics around indicating different kinds of failures. Now, it could be used in MBSE, and we'll see an example of it. It's nice because it is graphical, so it lends itself to a modeling environment, and so is a good thing that we could incorporate into an MBSE environment. It does provide a nice mechanism for identifying where you could mitigate a hazard by breaking the chain using some sort of safety design technique or eliminating the fault altogether, those sorts of things. And of course, performing one means that you're really focusing on that aspect of the system, which in and of itself is a good thing. There are some concerns or limitations, specifically if we're looking at this from a system point of view where we might not have a design yet. It has some specific issues around handling. It's not a technique to handle time ordering of events, so it doesn't handle that particularly well. And it's most effective when you apply it to a complete design, right? So you have to have a design to decide, what are the combinations of things that could lead to a hazard. And so when you're at a systems level and you may not have much detailed design, this technique starts to break down a little bit. The other thing is that you are typically focused, you select a hazard and then build the tree. So it's not a technique for identifying hazards, it's a technique for analyzing how you can get to a hazard. So there is the other element that is as important, and that is defining and finding the possible hazards of a system. Now, there are other types of techniques that are similar. The event tree analysis, which is used in the nuclear industry. Here you start with an initiating event of some sort, some element fails, and then you follow a set of branches that enumerate what are the possible outcomes of that failure. So it's similar to FTA in that you do require in order to perform it, you have to have the system there, so it's a technique that's applied to a design that exists. And of course, in an MBSE environment, we are concerned with developing a design. So again, it suffers the same problems that FTA might have. There are a whole other set of techniques out there that you may or may not have heard of. FMEA and FMECA are actually not even really safety analysis techniques. They're reliability analysis mechanisms, which have their importance, of course, but if we're focused on safety, they're things that are related but not something that we would use as a primary mechanism to ensure safety in the system. All of these techniques suffer from problems around their point of view of safety. And today's systems now exhibit properties that make them less effective than they had been when they were first developed in the 60s and 70s. So if we looked at a concept of complexity in terms of differentiation and integration, differentiation meaning the number of elements of a system. So the more elements you have, the more complex it is, and that's pretty obvious. The other dimension is integration, and that is the amount of interaction between those elements. And this is where today's complexity is being driven from in today's complex systems. So in today's system, behavior, more often than not, is being driven by the interaction of the components as opposed to the individual components themselves. And this includes, of course, unsafe behavior. This is enabled by the use of software in these components so that component A and component B can be connected together through some sort of communication mechanism and have a very high level of coupling in terms of the behavior that they produce between themselves. The other thing is that this connection, this integration mechanism, is not physical in nature, so it's difficult to look at and analyze as opposed to a purely mechanical kind of system. And this is where these traditional techniques have problems, because most of them are based on the concept of a failure, as we discussed earlier in the definition, as opposed to dealing with things with errors, design errors, and things like that. Let's look at an example that illustrates that. So this is a real example. I think this was an English chemical plant of some sort. There's a reference to this example in the back here that the references. But essentially what we have here is a computer-controlled batch plant where we have a catalyst that is controlled by a valve, the amount of catalyst that enters into a reactor. The reaction produces vapor pressure, which is then run through a condenser to send it back to the reaction. And that condenser capacity is driven by a valve that lets in a certain amount of cooling water to manage the capacity of the condenser. It's a very simple sort of diagram here. So there was a requirement for the computer that if a fault occurs in the system, that we would just leave the plant, all the variables where they're at. In other words, leave the valves where they're at, just leave everything, sound an alarm so that the attendants at the plant could address the problem. And so what happened, there was a low oil signal detected in this gearbox. The computer did exactly what it was asked to do. It sounded alarm, and all the variables, all of the control of the computer was handling was held as per the requirement. Now at that time, catalyst was being introduced to the reactor, so the valve here was open, allowing catalyst to enter. And at the same time, the cooling had not it had barely been open, and so the condenser was getting a small amount of water. And so while the system was held at these states for someone to take care of this, the reaction continued, vapor was produced, and the condenser couldn't manage the capacity there, and so it ended up venting a hazardous substance into the atmosphere. So the thing to note here is that, and this is the crux of what we're getting at, is that everything here worked exactly the way it was supposed to, including the software. Nothing failed in any normal sense, in the sense that most people think. And so any technique that you would look at to increase the reliability of any of these components would have no effect on solving or addressing this particular problem. And this is the kind of systemic kind of failure, the system failure that the traditional techniques have problems with. Now, there are and have been some approaches taken by certain industries. The chemical industry created this HAZOPS, which is really kind of a systemic analysis technique for a a chemical system or a plant processing system. It's a process kind of thing. The key things that it uses is that it uses these guide words. So one thing you're doing here is you're analyzing the system and you apply these guide words, like for instance if you've got no flow in a pipe or the valve doesn't open, those sorts of things. The key here is that you're identifying hazards, right? This is a technique that allows you to identify hazards in the first place. So I mentioned you view things as deviations in parameters in the operation of the system. It's fairly simple to apply. Of course, you need expertise in the system to do it, but that's fine. It is simply just a table, so it's not inherently graphic, so it has some limitations with a model-based focus. And you do need a general representation of the system to guide you through using the guide words. There are some new techniques out there, STPA, System Theoretic Process Analysis. This was developed by Nancy Levinson. It is an approach that is inherently rooted in a systems focus, a system engineering approach. Instead of viewing safety as failures of things, it views safety as inadequate control over a process. And so there is a graphical model that it guides you into thinking about the different ways you could lose control over something. Of course, it's the nice thing about it is because it's system focused, it can be used on very abstract concepts. So very early on in the systems engineering phase, it has this explicit mapping to the to hierarchical decomposition that's typically done when you develop a model or a model-based system engineering environment, where you start at a sort of high-level black box level and you're decomposing and allocating. And it uses these guide words, so it's a good tool for identifying hazards and then later perhaps analyzing in more detail with an FTA. Of course, this is relatively new, so it hasn't been used nearly as much as other techniques, and so the question is, how effective is it? There's some evidence that it has been very effective in certain cases. The other thing is that you get maximum benefit with it when you effectively use traceability in your environment. So, and that's really true for all of these, and as we'll see in some examples, that's a major advantage of using these techniques in a model-based environment, is you're given a mechanism to produce traceability. So if we think about maybe some goals for incorporating these hazard analysis techniques in our MBSE environment, obviously we want to be able to leverage the graphic and semantics of SysML itself. So we incorporate it directly with our systems model. We also want a sort of a framework to think about which kind of technique, whether we're using fault tree or not, but a framework in which we can determine what would be the best one to use for the particular information we have at hand. Of course, we want to be able to have a mechanism to create traceability between our design artifacts and the artifacts used in the safety analysis. And also, of course, work with and support the current kind of MBSE development approaches that are out there. There have been and there are FTA profiles available for use in a model-based system engineering environment. So typically what we do is we create a profile in a SysML profile that allows us to specialize SysML elements as specific kinds of safety analysis elements. In this case, and in OR gates, the concept of basic faults and other elements that are used in an FTA, and then create a diagram type. And then what we can do is create FTA diagrams which show a fault tree and then associate them. In this case, we see them associated dependencies to individual requirements. So the nice thing about SysML is that we can have textual requirements incorporated into our model. And then we can create as many kinds of views as we want in our modeling space. So again, here's another fault tree, but in this case, we have traceability to design elements. So particular sensors or controllers and so forth that either mitigate faults or are the producers of faults, or a place that might actually cause a fault. And this has been around for certainly in our tools for a good amount of time. If we think about incorporating stuff, maybe perhaps higher level elements, and this is newer kinds of stuff, maybe incorporating thinking around systems-focused safety. Of course, we'd want to start at the very top, the use case. And the use case is important because it really sets the context of the system. And the context, as we'll see in a quick example, goes a long way in framing the problem and then hence defining where hazards should be considered or not. So we would want then to perhaps create an element called a hazard that we can model with a description and whatever appropriate other information we want to associate with the identification of a hazard. And then, of course, we want traceability to the use case that it's perhaps associated with. The other concept that's useful is a safety design constraint. Some folks might view this as just a specialized kind of requirement. I mean, it could be, but I think there's value in explicitly separating it from a requirement. So it's a design constraint, some sort of constraint based on mitigating a specific kind of hazard. So that there's an association between these and hazards that are identified. And that design constraint then can be tied to some description of behavior or element in our design, which is sort of abstractly represented by this block here, and that the design must satisfy the design constraints, which are driven by hazards. So you can think of this in the context of, say, the black box level of our system. And one of the things that we typically do in system engineering is go through the process of decomposing from a higher level extraction to more detailed. And so we need to be able to cross that boundary, and you would essentially carry on. You would develop, for instance, as we move from a design level, we allocate. Allocation is typically a term used in SysML to allocate behavior from one level down to another level. You would have corresponding hazards derived from higher level hazards. So as we gain more insight into our design, in other words, we introduce architectural decisions, technology decisions, and so forth, we essentially want to restate our hazards in context of those decisions. So that's really what we're doing here when we derive a hazard. And then again, restate the constraints that we have identified in the context of the decisions that were made as we move to that next level. So perhaps this might make more sense if we look at an example, which I'll go through here. So I need to switch over here, so bear with me for a moment. Let's see here. I'm going to switch my, there we go. And okay. So hopefully you can all see my screen. I think it looks like that came up. So again, starting from the use cases, as I mentioned before, this example is for an automatic people mover, one that you would typically see in an airport. So these are essentially driverless trains or horizontal elevators, and this is the subject of this particular example. And we'll focus here on loading and unloading passengers on the train for our example. So in this case, a use case, We have some stakeholder requirements that have been given to us. The people mover can be configured as a dual-lane shuttle with 4 stations, 2 terminals. That's important, as we'll see here in a second, because the configuration of the track has a big influence on the kinds of hazards we're going to identify. So, for instance, a single-lane shuttle has a bypass in the center, which creates a collision hazard that, for instance, a dual-lane shuttle does not have. And so these kinds of high-level, perhaps architectural system decisions or site decisions have to be considered right off the bat. Also, the trains are going to have automatic doors on either side for unloading and loading passengers. So an example of that, if you've ever been in Washington Dulles, there is a people mover that takes you from the terminal out to the main terminals. This is a configuration in which folks load in the center through one set of doors and unload on the outsides through other sets of doors. And again, this specific configuration is going to have specific hazards associated with it. So if we look back at our loading and unloading of passengers, what kinds of hazards could we think about? So, of course, exposing the passengers and personnel to moving trains and power sources, right? So this would have to do with the terminal itself and how we barrier them against that. We don't want folks on the train to be able to expose themselves to the train structures during movement and so forth. So these are very high-level, black box, use case level kinds of hazards that we're going to start with. So if we go back to our use case, one of the things we would typically do once we've identified, say, some main hazards is to describe this use case in a little more detail. So here's a simple activity diagram which talks about the train stopping at a station, opening the exit doors and train doors. We can see we have requirements that have been tied to these particular actions and so forth. Obviously here the trains will have automatic doors on either side for loading and unloading passengers when we do open the exit doors. So this would be a typical system engineering activity. We would then come in and define an architecture. So this is now moving from a black box view of our system to a white box. What are the components of our people mover? Well, we have guideway, we have trains, and so forth. If we focus here in on a train, the train contains a vehicle, in fact 2 vehicles. The vehicles have doors, they have AV and climate control, etc., etc. So the components. We've introduced components into our system, and what we want to do is restate our requirements, our hazards, in the context of these new elements. I need to do this here. So here is an example where we've taken the high-level hazard H2 and derived a new hazard. So we're talking about exposure of passengers to impact, but because we know we have train doors on the train, this really could be stated that the doors cannot open while unless the train is sitting in the station properly aligned. In other words, at all times the doors are closed unless it's at a station with the train aligned, which give rise to a whole bunch of design requirements, right? The doors must not open without the train aligned to the station. The station doors must not open from passengers or baggage leaning on them and so forth. So these are specific statements of our constraints that you would apply to our design based on mitigating this particular hazard. And so we can create a diagram that looks just like that. Notice here that the derived hazard is driven by a stakeholder requirement in this case. This also could be an architectural analysis, maybe a trade study that decided that that we were going to implement some technology this way. So essentially what we're doing is we're saying we've derived these hazards and based on decisions that we made in our design space. And this becomes important when we do traceability, because we want to know the high-level hazards, the derived hazards, why we derived those hazards, and the resulting design constraints. And as we'll see later, in the next slide here, we then want to relook at our activity diagram, except we've overlaid now the architectural elements, the fact that we have a train, that we have a central control, that we have station doors and so forth. And we want to then apply the design constraints in terms of traceability. So here we have the train that enters the station. We need to confirm train alignment. Well, the train doors must not open unless the train is aligned. I'm not saying how we're going to do this yet, but it's got to satisfy this constraint ultimately. And as we get into the detailed design, we would want to trace down specifically what we're doing to make this confirmation done that satisfies our risks. The same with the train when it's sitting at the station with the doors open. We want to monitor the movement of the train actively the whole time. So you can see the idea here is that as we move from more levels of detail, we want to carry with us all of this hazard information to give us a view of how we're mitigating the hazard right from the beginning. We want to bake this in from the beginning and not apply safety or an analysis after we've done the design. If we head way down to the design of the actual doors themselves, where we've identified that there are several components, a controller and so forth, door sensors, door locks, and what have you. Perhaps we even have behavioral models and state machines which describe their high-level behavior. So we have some much more detailed information. Perhaps at this point it's a good time to do, say, a fault tree analysis where we have the hazard, and again this hazard has flowed down from the top, from the use case level very specifically, and we have a trace tree of where this came from. We're not just arbitrarily picking this. I think this is one of the keys. So we can look at we can build a fault tree analysis. It can be tied then to specifically to design elements. So we have a door obstruction sensor which perhaps could fault, and that will be one of the causes that the passengers might get hit by something, by the doors while they're closing. Or for instance here, the door controller, for instance, has a fault, would be another possible reason why this might occur. And so the fault tree gives us very explicit traceability between the elements of the design that could fail and cause and lead to this hazard, and we have a traceability of where this hazard came from and why is it there. And I think that's the key element here. So let me switch back to our presentation. Let's see here. I think should be able to. Okay, so in summary, the complexity that's being driven now in many of today's systems, that is the interactive complexity that we talked about earlier, it limits the effectiveness of traditional kinds of safety analysis techniques that are really based on this perspective of something failing. There are new approaches out there that are focused, that have a different perspective, that take a systems point of view, so that we can start thinking about safety from the very early design point and not address it later after the design is complete. The nice thing about MBSE is that it can incorporate many of these kinds of analysis in one tool. And in fact, a development process gives us this framework that allows us to use system-based sort of approaches to safety on the early stages, and as we get into detailed design, we could perhaps use the more traditional approaches where they're most effective. And then, of course, traceability. This is a big deal. Having an environment, an MBSE environment, where traceability is inherently part of the environment, so that creating traceability is easy. You do it in context, and then, of course, later you're able to aggregate all that information, federate tables which show complete traceability between the highest level hazards right through the different levels of abstraction. So you have this one-to-one correspondence between the evolution of the design and the rationale for the design and the consequences of that on the hazards and the design constraints that are associated with them. There's some really good references. I mentioned Nancy Levinson and her systems thinking approach applied to safety. She has a book out that's an excellent reference if you want to learn more about her technique and thinking about safety from a system engineering perspective. She also did quite a while ago a book called Safeware, which is about the use of software in safety systems. Also excellent. Lots of good concepts in there that are directly applicable today. My colleague Bruce Douglas from IBM Rational produced actually the FTA profile that is used in our Rhapsody systems engineering modeling tool, and it actually includes not only FTA but some security kind of diagrams also in it. And then there's some references there to the APM standard that I used. So that's all I have. I'll open up for questions right away if you want to do that.
Gavin, we do have some questions. The first question is, a gentleman is asking how to handle the fault of observer not understanding the system, and then he's saying the failure was presuming rational requirements. Does that make sense?
Well, I'll try to answer that.
Okay.
We can go from there. Yeah, the whole subject of human-machine interaction is it really is a subject in and of itself, and there are books and techniques specifically on that. I admittedly didn't specifically include those in what I showed here, although in a general sense some of the guide words that are used in some of the techniques account for improper user interaction. In other words, you think of a person as if the person is considered part of the system, and in some safety analysis this is quite appropriate, then they are just an element, and there's an interaction and interface that exists between that person and the system that needs to be looked at. And certainly the technique there I referenced, STPA, does allow you to use that. I mean, there's no limitation there. And of course you could then add that to the model. But there are some other, I think, unique features of human-machine interaction that are beyond the scope of even just modeling. I mean, it's a cultural thing, and while it's I think an important subject, I didn't specifically address it here. So, in this context, I think I'll leave it just at that.
Okay. The next question is, does this people mover use case, hold on, I can't, does the people mover use case, describe, or prescribe?
So I'm not sure exactly what that question means. One of the things, yeah, one of the things in certain industries, like people movers would probably be a good example, but there would be others which are regulated. There are typically standards out there which describe or prescribe specific ways in which known faults are supposed to be handled. So in that case, in the example I gave, that people mover model, which was really a simplistic form, you probably would have a set of standards, the APM standards, which drive a lot of the design decisions. And in that case, they would in a sense be the rationale for why certain decisions were made around the technology or the technique used to handle some hazardous situation. So as you derived hazards, you would, instead of being a trade study or a user requirement, the rationale might be a reference to a particular portion of a industry standard. That is the reason why you did certain things. And again, the idea here is that you have this link between the industry standards, your requirements, your general requirements, and the design decisions that you make internally as a result of doing the project. So you could produce documents that, for instance, show every element of the standard and the things that are there covering it or mitigating or satisfying those elements. I hope that answered the question.
Great. Okay, I don't see that there are any other questions. At this point, I'd like to say thank you for participating. And again, to remind you that there will be a recording of today's webinar and a copy of the presentation. It's available on the OMG website, which is www.omg.org. Give us a day or two to get that up, but it will be up there. And what we'll do is you'll be getting a follow-up email with the link to that address. And as a final note, I'd like to extend an invitation to all of you to the MBSE in Healthcare Summit on June 18 in Boston. The event is co-located with the OMG Technical Conference at the Omni Parker House Hotel. And you can get further information and register for actually both events at www.omg.org. Go to the calendar section. You'll see the OMG Tech Conference listed, and then you'll also see the MBSE and Healthcare Summit listed as well to the right. There will be a link, and you can click on that, and you can register very easily and quickly. So I think that's about all for the moment, but again, to remind you to look for a follow-up email with the link to the presentation. And I think that's about it for now. Is there anything else you wanted to add, Gavin?
No. I think in addition to the link to the presentation, there probably will be some references to some other resources that we have, both webinars and other things that will be available.
Okay. Well, thank you so much. Hopefully we'll see you again. We plan to do more of these types of programs, so thank you again. Bye-bye now.